Hey everyone, welcome into lecture number 5. This lecture is on the fundamental existence and uniqueness theorems, and there are two of them. So let's start by stating the first one. The first one is going to be the theorem for linear first-order differential equations. Alright, so it's going to be the theorem. It's going to be the FEUT, fundamental existence and uniqueness theorem for linear equations. So I'll call this the FEUT-L. This is how we'll refer to it moving forward. But again, it means exactly, these letters stand for exactly what I've just said. So it's fundamental existence and uniqueness theorem. And this one's special. This one's for linear first-order differential equations. Really for linear first-order initial value problems, but we'll see when we state this that there has to be an initial value problem. So let's state our assumptions, and then we'll state the conclusion of the theorem. This is the following: if the functions p and g are continuous on an open interval. So an open interval, we'll call it I, in case we need to refer to it later, but I is just going to be the interval, let's say it this way, use a colon, alpha less than t less than beta. So the interval from alpha to beta, it's open, meaning that it doesn't contain the endpoints, right? And the only other restriction here is that this interval must contain the point t equals t naught. So t naught is going to be the initial point in our initial value problem in a moment. So these are the assumptions. These are the only assumptions, actually, that our functions p and g are continuous on this open interval, and that the open interval contains the point t naught. Okay? And so here's our conclusion then. Then there exists a unique function. So this takes both of our words into one sentence here, right? So then there exists, that means we can find it, right? But it exists. A unique function, and this unique means there's only one unique function, y equals, I'll call it phi of t for solution notation, that satisfies the initial value problem. Alright, and the initial value problem is going to be just this. So it's a linear equation. So that's where the p and the g come from, right? So the initial value, the differential equation in the initial value problem is going to be linear. It's going to be y prime plus p of t y equals g of t. So there's our linear first order differential equation, and the initial value is just y of t naught is equal to any value y naught. So that's very interesting, right? It's equal to any value y naught. So this right here is our fundamental existence and uniqueness theorem for linear first-order differential equations. It says that for us to know that a unique solution exists, meaning that that there's one answer, and that that one answer is it exists, and we can find it. All we have to do is check that the coefficient functions in our linear differential equation, our p of t function and our g of t function, are continuous on a common interval that contains our initial value. All right, not our initial value, sorry, our initial point, our initial t value, initial point. So t naught. So we just have to check our p and our g and make sure that they're continuous at this point t naught. If they are, then a unique solution exists, and it not only exists, but it exists on the entire interval that these two functions are both continuous on simultaneously. All right, so that's huge. Now, the existence and the uniqueness parts of this theorem are both important, okay? They're both very important. So I've kind of talked about this already, right? But the reason that we like to check for existence is that if you know that a solution exists before you try to find it, then you know that it's not a waste of your time to put in the effort to try to find the solution, right? It exists. If you put in the work, right, then eventually, hopefully, you'll be able to find the solution because it does exist. The other half of that problem, though, is say you put in the work and you find a solution, you want to make sure that it's the solution, or it's at least the correct solution, right? And so that's where the uniqueness comes in. So this says that after you've put in the work and found a solution, that solution is the only one. So therefore you found the solution that you were looking for, right? The exact solution that you were looking for. All right, so that's why existence and uniqueness are important, because they're kind of work that you can do before putting in all the effort to try to solve this initial value problem, to ensure that the work is worth it, right? And this comes into play when you're using computers to try to solve these or approximate solutions to these initial value problems. It's always good to know that you're not wasting your resources. Okay, so we'll talk about existence and uniqueness theorems a lot moving forward. Let's talk about the sketch of the proof for this linear version. So this is a theorem. All theorems should be proved when possible. Now, it's not necessarily within the scope of this class to prove every single thing that we talk about, but we'll at least talk about how to prove the things that we can prove. And so this this one is a problem that we've already found a general solution to, right? So we already found the general solution, and really this theorem now just tells us that the general solution we found both exists and is unique. So let's just go through the ideas that we've already remembered, right? So I call this a sketch of a proof because I'm not going to write every single detail, but you guys should fill in the details of this as you work through this lecture. But recall that the general solution, so the general solution of a first order linear differential equation of this form, y prime plus p of t y equals g of t, is given by an integral equation, right? It's given by this equation. We'll call this phi. Phi of t is equal to, remember how this worked? It was 1 over mu of t, integral from something to, so I'm going to leave this blank for a moment, but integral of mu itself of s times g of s ds, all right? And then there's usually plus c, and we could write this all like this. The 1 over mu can get distributed here. And at this point, we should remember, right, what the mu is. So the mu is the integrating factor, and this is defined in terms of p. So mu of t is equal to the e to the integral p of t dt. So at this point, before we go any further, let's just notice that in our assumptions, so we get to assume when we're writing a proof, we get to assume that our assumptions up here hold, right? So, all right, if the functions p and g are continuous on an open interval I containing the point t naught, right? So that's what we get to assume. So our function p is continuous on this interval. And since p is continuous on this interval, then it is integrable, right? And the exponential of it is also continuous on this interval, just because of the properties of continuous functions and exponentiation and integration, right? So this function, so now we'll say this over here, mu is continuous on this interval from alpha to beta, since p is assumed to be continuous on the same interval, right? All right, so there we go. Now we've got our mu is our continuous function. We've also talked about in the past when we talked about this general solution that our mu, this integrating factor, is positive, and so this right here, the dividing by mu, is not going to be an issue, right? All right, now the way I've written this now, this is the general solution. We have not dealt with the initial value, right? So to satisfy the initial value, we can apply, we've done this in the past as well, we can apply the fundamental theorem of calculus, right, to make this integral more exact in some sense, to clarify exactly how this interval should be behaving. But to satisfy the initial value, which remember was y of t naught equals y naught, we can use the fundamental theorem of calculus, and we can write this as follows then. Our phi of t now can be written as 1 over mu of t times the integral from t naught to t. So this is where the fundamental theorem comes in. All right. And what's going to happen here? Well, this is still just integration variable. So there we have that. And then we have our unknown constant here. So I'll leave that for a moment. But the first thing we can do is get this in here, right? And then from here, we need to determine what this C should be. So our phi of T naught on one hand should satisfy this initial condition, right? Should equal Y naught. But on the other hand, it's going to equal 1 over mu of T naught times the integral from T naught to T naught, which of course that part's going to be 0, right? Plus C. And so this part is 0, right? Because the integral doesn't go anywhere. It's from T naught to T naught. And so this leaves us then with this equation. Y naught is then equal to C over mu of T naught, and therefore our constant is going to be Y naught plus mu of T, times mu of T naught, sorry. Okay, so now multiplying back through, if we multiply through and get rid of these parentheses, then we'll see that these mu of T naughts will cancel, and what we end up with for our solution is this equation. So phi of T, our actual solution, is going to be 1 over mu of T, integral from T naught to T of mu of S, G of S, ds plus y sub 0. Okay, and so this is our this is our particular solution to the initial value problem that we were given. Again, we've done this before, but it's nice to work through it every once in a while just to remind ourselves. So there we go. There's our solution to the linear initial value problem, and everything here was determined by the functions p and g. Okay, so we've already talked about this. Mu is continuous; it's not 0. This integral is also going to be continuous because it's a product of continuous functions, right? So let's just state it. So mu of s, or mu, I'll just leave off the arguments, but mu times g is continuous on the same interval from alpha to beta, since p and g are, right? Since they're assumed to be. And therefore, the integral makes sense, right? This is the key. It turns out it's continuous, but it's not only continuous. It just exists, right? So this is continuous as well. It's a well-defined function. All right, and so the uniqueness follows from, so the existence is that, okay, we've written down the answer, right? The uniqueness follows from all these choices that we've made. They give us this precise, this one function. This is a single function. Okay, so there's a sketch of the proof, but the whole idea here is that the proof of the linear version follows from our general formula for the solution that we determined back in a previous lecture, right, on the lecture on the linear differential equations, first order differential equations. So let's leave this here. You guys can fill in the details if you want on that. I recommend that you at least work through everything that we did and make sure that everything we've done makes sense. But this is the solution to our linear initial value problem. So let's look at an example next. Let's say we have the following initial value problem. Consider this initial value problem where the differential equation is ty prime plus 2y equals 4t squared. And the initial value, we're going to change this, but let's start with the initial value being y of 1 equals 2. And the question that I want to know here is first of all, so a couple questions. Number one, does a solution exist? So can we find a solution? And if so, on what interval is the solution defined? All right. So let's start with question 1, right? Question 1 is obviously more important. We can't ask, well, we can, but there's no point asking the second question if the first question's a no, right? The first thing we do is when we look at this equation, we notice that this differential equation is linear, right? But it's not in the right form. So for our fundamental existence and uniqueness theorem to apply, this has to be in the form of y prime plus p of t times y plus g of t. So the first thing we have to do is divide through by t and get this in the proper form, right? So when we divide through by t, we end up with y prime plus 2 over t times y equals 4t. All right, and now, only now at this point, can we identify our two functions, right? Our p and our g. So our p of t in this case is 2 over t, and the domain of p is just, I'll write it in interval notation, but negative infinity to 0, union 0 to infinity. You just can't have 0, right? Can't divide by 0. And our g of t is going to be equal to 4t. The domain of g is all real numbers, right? No restrictions on this linear function. So, by the way, these are not just the domains. These are because this is a rational function and this is a polynomial, these are the domains where they're also continuous, right? So p and g are continuous on their domains. And that's the key, because the fundamental existence and uniqueness theorem doesn't just ask for the domains, it asks about the continuous, right? Them being continuous on their domains. Okay, so once we've done this, now we can compare with our initial values. So we go back and we see the initial t value here is 1. And of course 1 fits in the domain of each of these, right? So p of t is continuous from 0 to infinity, 1 is in there. G of t is continuous on all of R. Obviously 1 is a real number, so that fits in there. And so we can conclude then, right, that the fundamental existence and uniqueness theorem says we have a unique solution, all right? So the FEUT linear version applies, and there's a unique solution. All right, and then the other thing that we learned from this is that the domain of the solution is the largest interval on which both of these are continuous. So the domain of the solution, the interval on which the solution is defined, is going to be the interval, the overlap, essentially, of these two domains, right? And so it's going to be, the unique solution is going to be defined from 0 to infinity. All right. So it's going to be defined on this interval from 0 to infinity. So we can find the domain of our solution of a linear first order initial value problem without even solving the problem. We didn't actually have to solve this, right? We know how to do it. We would have to plug into this formula, right? But we didn't actually have to do it to find the interval of the solution, the domain, basically, of the solution, right? All right, what if we change the interval, or sorry, what if we change the initial value? So the initial value, what if this is changed to y of -1 equals 2? Do we still have a solution? Yes, well 0 was the only bad number, right? So 0 would be the only t value that we cannot allow, that we would say, okay, the FEUT does not apply, right? There's no solution. And you can see that if t is equal to 0, by the way, the initial equation just says 0 plus 2y equals 0. So, you know, it's not that there's no solution. It's just that it's not the differential equation anymore, right? So we have to be careful saying there's no solution. But what we can say, though, is that if t is equal to 0, t naught is equal to 0, then the fundamental existence and uniqueness theorem does not apply, right? Does not apply. However, that's not what we're looking at, right? We're talking about -1. So if t is equal to -1, it does apply. And look at the difference now. So now we take a look and we see, well, this time our interval, right? -1 is in the interval on the left-hand side of this kind of broken interval here of the domain of p. It's on the left-hand side. And so the fundamental existence and uniqueness theorem does apply, but the interval is going to be different, right? So the FEUT-L still applies, and the domain of the function of the solution, will say, this time is -infinity to 0. It's a negative half of the real line. Okay, so here's one for you guys to try. Let me just write it down. So the idea here is, the question is, I'll write the questions first and then I'll write the initial value problem, but does the FEUT linear version, does it apply? And if so, what is the interval, the smallest interval guaranteed by the FEUT for the solution to exist? So let me say it this way. If so, find an interval on which the solution is guaranteed to exist. All right, so here's the initial value problem. It is natural log t times y prime plus y equals cotangent of t, and the initial value is y of 2 equals 3. Okay, so take a moment to work on this one on your own, and I'll check back with you in a minute. All right, now that you've had a chance to work this one out, let's take a look at it. In this case, this is very similar to the last one. It's not quite in the right form, so the first thing that we need to do is divide through by this natural log and write our differential equation as y prime plus 1 over natural log of t times y, and then this is going to equal cotangent t over natural log t. Now, despite the fact that we have a formula for solving any linear equation, this is not one that we probably it doesn't look like it's going to be a nice one, right, to actually solve, but we can still apply the fundamental existence and uniqueness theorem. So here's our function p of t on this side, and on this side here's our function g of t. All right, and so we can look at their domains. So the domain of p, first of all, the natural log only takes in numbers from 0 to infinity to begin with, right? So the domain of the natural log is 0 to infinity, not including 0, positive numbers only. And we can't divide by 0. Log of 1 is 0, right? So t is also not allowed to be equal to 1. And so what we end up are these two intervals, so from 0 to 1, and then from 1 to infinity. So that's the domain of the natural log. Cotangent is defined, it's periodic, right? It has asymptotes at 0, pi, 2 pi, 3 pi, etc., right? So for this one, we have g. I'll just write the things that we can't equal, right? So t cannot be equal to 0, pi, 2 pi, 3 pi, etc. And it also cannot be equal to 1 for the same reason here, right? It's got to have the same, because of the fact that it's got the log, it's got to have the same restriction, except it's got more, right? So it's also, t must be greater than 0 because of the natural log. Because really, what I should have written here is that t cannot be any multiple of pi for the cotangent function for any z, right? It can't be equal to 1 because of the log, and it has to be positive because of the log. Okay, so there's a whole bunch of restrictions on the domain here. However, we are only concerned with the domain near 2, right? So near 2. All right, so 2 is between 0 and pi, it turns out, right? Pi is around 3.14159, etc. But so 2 is between 0 and pi. All right, but remember, that's not going to be good enough, right? So actually 2 is between 1 and pi. The point is, it's not equal to pi. It's not any of these restrictions, right? So actually, our functions are defined at this point, and they are continuous because they are, they might not look like nice functions, but these are nice functions. So these are continuous on their domain, and so therefore, we can say that p and g are continuous, right, on an interval containing 2. So an interval containing t equals to 2 or t not equal to 2, and therefore a solution exists, right? So the FEUT applies, and a solution exists. So then the interval guaranteed, the guaranteed interval is then going to be what? Well, it's got to be the interval that contains 2, right, after all of these restrictions. So it's going to be, we kind of talked about this already, right? It's going to be the interval from 1 to pi, right? So the guaranteed interval is the interval from 1 to pi. And that's guaranteed interval for the domain of the solution function. The domain could be larger in certain cases, but we can't guarantee that, right? So all we can guarantee is that the domain is at least this interval from 1 to pi. Okay, so that's how that works. All right, now we're ready to talk about the general version, or what you might call the nonlinear version of the fundamental existence and uniqueness theorem. So let me state this one. So item number 4. So this is our fundamental existence and uniqueness theorem, the general version. So I'm just going to label this as FEUT-G for our general version. And it's going to say the following. So let's let, in this case, the functions. There's going to be a function, and we're going to take a derivative of this. But let's let the functions f equals f of ty and df by dy. These curly d's mean this is a partial derivative, and I'll tell you exactly how to compute this in some of the examples moving forward. But basically, this is the derivative of the function f with respect to y, where you ignore t and you just treat t like it's a constant. Okay. So we'll do an example where we see exactly how this works. But these two functions, let's let these be continuous. Now this is a function of 2 variables, so this is going to be continuous on an open rectangle containing our initial value. So the rectangle we can define as follows by 2 different inequalities. So t is going to be between alpha and beta, just like before, and our y value is going to be between gamma and delta. So there's how we get the rectangle, right? And the whole idea is that this rectangle should contain our initial point. So containing the initial point. This time we're going to write our initial condition as t0, comma y0 as a point in the ty plane. All right? This is our assumption. Again, the assumption's about continuity of functions, but this time the functions are more, well, they're just different, right? They look different. And the domain that we have to consider involves the y direction as well as the t direction. The linear version only involved the t direction, not the y direction, right? So here's our conclusion. And it's a little bit different than the one from before, right? So then on some open interval, t0 minus h less than t0 plus h. So here h is a small real number, small positive number, I should say. All right, and this interval has got to be contained in the original. So contained in alpha less than t less than beta. There is a unique solution to the first order initial value problem given as follows. This initial value problem is going to just be y prime equals f of ty. Looks simple, but remember in general this f could be very complicated, right? And the initial condition is exactly the one that gives us this point. So it's y of t0 equals y0. Okay, so there it is. That's the general version of the fundamental existence and uniqueness theorem, or the FEUT-G as I've named it here, but the general version, again, sometimes called the nonlinear version. So just a couple of notes before we move on. But this theorem applies to the linear version. The linear is more specialized, right? So this applies to linear differential equations, but the conclusion is weaker. So the conclusion says the unique solution, right? There is a unique solution. Or maybe you should even say that's right here. There exists, right? So that we get the words in there, but there exists a unique solution to the initial value problem, but the existence is only on some open interval. It's not on the whole interval, notice. This is a small sub-interval of this one, okay? So this applies to linear DE, but the conclusion is weaker. And so that's why there's a separate one for linear equations, because we can make a stronger conclusion for linear equation. All right. So there's one note. The other note is that the existence and everything here depends on the y value of the initial value. It did not, and for the linear equations, it did not depend on the y value, right? But this one depends on the y value. So the existence of a solution here depends on the initial y value. All right, so that's different than in the linear case. In the linear case, all the y values behave the same. It's just a question of where you are in the t direction, right? We've already talked about this, but the domain, an interval of the solution cannot be determined like we did on the previous two examples. We can't do it because all we're told in this one is that a subinterval, potentially very, very tiny subinterval, exists where the solution exists, right? So there's a tiny subinterval. But it's still useful though, because what we can say is that the solution exists near this point, right? But near could be very small. All right. Couple more notes before we move on, but here's an important consequence. So an important geometric consequence of both of these FEUTs is the following. So, important geometric consequence of our fundamental existence and uniqueness theorems is that solution curves cannot intersect because of the uniqueness, right? So in any point where the solutions exist, they have to be unique. That's what these theorems tell us, right? So solution curves cannot intersect, and therefore we say that the solutions of a differential equation foliate the ty plane. So they basically just break it up. Any point you pick will lie on one curve and only one curve, okay? Or it won't be a solution. There won't be a solution at all that passes through it. But any point for which a solution exists will lie on only one solution curve, and they foliate the plane. All right, and then finally, this information about the derivative. So what is this df dy? Why is this here, right? So what does this tell us? So the fact that this is continuous, the main thing that we're looking for when we check this, and we'll do this in examples as we move forward, but this being continuous means that the curve has not become vertical in some sense. And then there's other ways to interpret this as well, but means, I'll write it this way, means among other things, that the solution curve does not have a vertical tangent at this point. So remember, we did an example in a previous class where we had a solution curve that came in two pieces. It looked kind of like a curve this way, and from this point our initial value was around here, and in this direction we could only get to this point, right? Because on the other side of that vertical tangent, the curve kind of turned around. So the curve itself behaved fine, but as a function, right, we had a breakdown. So we had a breakdown of the function itself, but not necessarily the curve, and the same thing would happen here. So this derivative, among other things, it looks for points like this where the curve may become vertical. Okay, the solution curve's tangent may become vertical. All right, so we are not going to prove this in this class, this general version in this class, but later on in this lecture, we will talk about one of the main tools used in the proof. So we'll leave that for later. Let's first do some examples with some actual initial value problems. So here's item number 6. This one says, I'm going to write down the initial value problem, and then we want to check to see how this works. All right, so here's the initial value problem. This one's going to be in terms of y and x. So dy by dx equals 3x squared plus 4x plus 2 over 2 times y minus 1. And the initial value here is going to be y of 0 equals negative 1. So first of all, I want to know, does the general fundamental existence and uniqueness theorem, does it apply? All right, and yeah, that's really all I want to know on this one. So does it apply? So let's check, right? So what's f in this case? So f of xy is going to be equal to just the right-hand side. Notice this is nonlinear, right? But this is in terms of x and y instead of t and y. That's fine. Just change out the role of the t from the theorem, change it out with an x. So our theorem, or our function, is 3x squared plus 4x plus 2 over 2 times y minus 1. This is a rational function, right? Rational function. And so we know that for rational functions, the only thing that could go wrong, where our function would not be continuous, is if the denominator is 0, right? So I'm going to call this the obstructions. The only obstruction that we have is that the bottom, right, can't be 0. So y minus 1 cannot be 0. In other words, y cannot equal 1. But that's okay. We'll come back to this in a moment, right? But that's going to be okay for us. We're not going to have a problem there. The other thing that we need to check, though, is the partial derivative. It's called df by dy. So to do this, what we do is we take the derivative with respect to y of this entire function. All right. You'll learn about this in Calc 3 if you haven't had Calc 3. So this is, it's pretty straightforward. We're not going to get into the theory of these things. We're just going to talk about how do you compute them. And the way that you compute them is you take all the stuff that's not a y, right, that can be factored out in some sense, and just treat it like a constant, okay? And so we can ignore it. I'm going to write more steps here because this is the first time we're doing it, but we can just factor this whole term out and then just take the derivative of what remains with respect to y. So this is the derivative that we have to compute, right? And so at this point, we've got this function, 3x squared plus 4x plus 2, treated like a constant because it's not y, right? Those are all x's. By the way, it's not always possible to just get this out the way I've done it, but for this one we could, so we can do it. And then we take the derivative of this one. This is a chain rule, but it's pretty straightforward chain rule, and it just gives us negative 1 over y minus 1 quantity squared. And we just put this all back together, right? So our function, df by dy, this partial derivative function, is going to be equal to minus 3x squared plus 4x plus 2 quantity over 2 times y minus 1 quantity squared. All right, and then we do the same thing. We look for obstructions on this one. So the obstructions on this one is going to be the same, right? What's the obstruction? Well, again, the x's are fine. They're in the numerator. If the numerator equals 0, that's okay. Denominator cannot equal 0. So this term can't be 0, so again, it's the same deal, right? Y cannot equal 1. And so then at this point, we go back to our initial value and we check. Well, all x values work. There are no obstructions on x values, right? So this initial x value is fine. And the y values, we just need to check. If there could be many of these, right? You could have different obstructions for each one of these functions. You have to check them all, right? You have to make sure that none of your obstructions are met. And in this case, we're good to go, right? And so the fundamental existence and uniqueness theorem applies. So the FEUT applies. And therefore, a unique solution exists on some interval. So sometimes you'll see some interval, sometimes you'll see the interval written, well, it's always written kind of symmetrically, right? So even up here I wrote it symmetrically. So it's an interval h units away from the initial point, right? So in this case it's going to be from minus h to h, right? On some interval minus h to h, because the initial t value is 0. Or sorry, the initial x value is 0. So this is true for some h, I had to use some, so for h bigger than 0. The idea here is that this h could be very small, right? So even if this is very small, the point is, because it's an open interval, you have a little bit of room to do calculus here. You can take derivatives, etc. All right, now, based on all of the work that we've done, we see that we can change, if we were to change our initial value to something like this, right? So if we change the initial value to y of 0 equals positive 1, right? then we've hit our obstruction, and the fundamental existence theorem fails to apply. All right, so right here, just making this change of the y value, we see that the FEUT-G fails to apply. And, you know, in this case, maybe there's no solution, maybe there's many solutions. So at this point, you can't say exactly what part failed. Is it the existence that failed, the uniqueness that failed? Is it both of them that failed? You know, if a solution doesn't exist, it won't be unique. So, but the point is it fails to apply, and we can't then use that data, right? All right, so that's how these work. Now, by the way, that one equation was separable. We could have solved that if we wanted to and compared and you know, see what the solution is. But let's do that for a different one here. So let's now consider the following. This is the initial value problem. Y prime equals y squared. Initial value is y of 1 equals 0. So I want you guys to check the FEUT and then find the domain of the solution function, which in this case, by the way, that's as long as the fundamental existence theorem applies, right? So then find the domain of the solution. All right, so take a minute and work on this one, and I'll check back in with you soon. All right, now that you've had a chance to work on this, let's try it together. So in this case, the right-hand side is very simple, right? So f of t is just y squared. There's no conditions here, right? So this is continuous everywhere. And then the derivative function is also very straightforward, right? The derivative with respect to y is just 2y. And so these are both continuous at all points. Whoops, continuous at all points in the plane, right? Remember, the points are t and y in the ty plane. All right, so we should be able to solve this. Let's see. This equation says dy by dt is equal to y squared. It is separable, right? So this becomes, in our separableness, becomes 1 over y squared dy equals 1 dt. And then when we integrate, we get negative 1 over y is equal to t plus a constant. Okay? And at this point, we could plug in our initial condition if we want. So right now, we don't have a solution yet. We have a implicit solution, right? But that's okay. So we'll plug in our initial condition, which is y of 0 equals 1. So this tells us negative 1 over 1 is equal to 0 plus c. And so c is equal to negative 1. All right? And at this point, we can then write down our solution, negative 1 over y equals t minus 1, and then just solve for it, right? So what we end up with is our solution function, y is equal to 1 over 1 minus t. This minus sign can be used to flip the order over here, right? 1 minus t. All right, so there's our solution curve to this initial value problem. Very straightforward. But let's talk about the domain of the solution now, because that was the second part of the question. First, we checked it with the fundamental existence theorem. Now we need to find the domain. So the point 0 has to be in the domain of this function, right? So the domain of y could be equal to anything as long as t is not equal to 1, right? So t not equal to 1. And so in interval notation, that's going to be from minus infinity to 1, and in general, from 1 to infinity. But we have to take into account the geometry of the situation, right? So 1 is an obstruction, and we cannot jump over obstruction. So this is not the domain of the solution right now. The domain of the solution is only the part of the interval that contains, or the part of the domain that contains our initial t value. And our initial t value should be 0. So we keep this and throw this away, right? And so the domain of our solution is just the half, right, or the part of the domain on the left-hand side. But the domain of the solution is this open interval from negative infinity to 1. Okay? So by the way, the interval guaranteed, not guaranteed, but the biggest interval that you could get that's symmetric would be from -1 to 1, but the function continues, right? So we weren't asked about that. We were asked about finding the actual domain of the solution, and there it is, interval from negative infinity to 1. All right, before we get to the tool that we're going to talk about for proving that is used in the proof of the general fundamental existence and uniqueness theorem, let's do one more initial value problem. So we'll do this one together. So let's consider this equation of the form y prime plus 2y equals g of t. And then initial condition is y of 0 equals 0. But here g of t is going to be defined as a piecewise function. So it's equal to 1 when the t values are between 0 and 1, and then it's equal to 0 for all t greater than 1. All right, we want to try to solve this initial value problem. So what we have to do is the following. We have to take this, because our right-hand side function is defined as a piecewise function, we have to take the pieces independently. So we have to think about this piece first, and then make a new initial value problem for the second piece. So let's see how this works. So on the interval from 0 to 1, right? Then our differential equation is y prime plus 2y equals 1, and our initial condition is y of 0 equals 0. All right, and we just want to solve this. So let's do it. We know exactly how this works, right? So we can use, this is a linear equation. We can use our integrating factor method. So our mu is going to be equal to e to the integral of 2 dt, so this is e to the 2t, right? Our g is just 1, and so our solution is y, and we have our initial conditions here too, right? So y is equal to e to the minus 2t, 1 over mu, integral from 0 to t of the mu, so e to the 2s, times g, 1, ds, plus, remember our general solution here, we've been able to factor out, get our 0, or our y naught, right? Here is a 0. And so here's our solution. We can integrate this though, right? So our y is going to be e to the minus 2t times the integral from 0 to t of e to the 2s. So the integral of e to the 2s is 1 over 2 e to the 2s from 0 to t. So this is e to the minus 2t times 1/2 e to the positive 2t minus 1/2. All right, and so here's our solution on this first interval. So our y is equal to, these cancel, right? So it's 1/2 minus 1/2 e to the minus 2t. All right, and so this is our solution on the interval from 0 to 1. Okay, what do we have to do next? Well, now we have to solve a second initial value problem for the rest of the solution. So at this point, everything's going to change. We're going to get a different function, right? We're going to have to paste our functions together somehow, our solution functions together. So now we need to consider, all right, at t equals 1, something's going to happen, right? So let's see. What's y of 1? We want to make sure that these match up. So we need to find our new initial condition, our new initial value. We get by plugging into our solution function here. Let's call this y1. All right, so y1 of 1, when t is 1, is going to equal 1/2 minus 1/2 e to the minus 2. All right, so that's what happens when t is equal to 1. All right, and then let's see how this works. So now our new initial value problem, is going to be this. It's going to be y prime plus 2y equals 0, right? That's what happens at 1, equals 0 now. And our new initial condition is going to be this. Y of 1 is equal to 1/2 minus 1/2 e to the negative 2. And we just solve this, right? So this one becomes y prime equals negative 2y. We separate, so we get 1 over y dy equals negative 2 dt, right? Integrate, this gives us natural log y equals negative 2t plus c. So y is equal to some constant times e to the minus 2t. And then we use our initial condition to solve for this, right? So on one hand, y of 1, this is y2 now, y2 of 1 is equal to 1/2 minus 1/2 e to the minus 2. And on the other hand, it's got to be this, right? c e to the minus 2. And then we try to solve for c. So just multiply through by e to the 2. And so we get that our constant here is going to be equal to 1/2 e to the 2 minus 1/2. And our solution then, y2 of 1, is going to be this number, 1/2 e to the 2 minus 1/2 times e to the minus 2t. Right? And then when we multiply this out, we get our y2 of t, this is of t, y2 of t is going to equal 1/2 e to the 2 minus 2t, right, minus 1/2 e to the minus 2t. All right, so now we need to plug all this together because this is only the solution for t greater than 1. All right, this is only the solution for t greater than 1. At t equals to 1, these two match up. They're the same, right? And so our general solution to this equation, or our particular solution, I should say, is a piecewise function. Our right-hand side was a piecewise function, right? And so we get a piecewise function here. On one hand, it's equal to, here it is, it's 1/2 minus 1/2 e to the 2t, right? 1/2 minus 1/2 e to the 2t. It's e to the negative 2t. Be very careful when you copy here. And this is for t between 0 and 1, right? And then it switches and becomes 1/2 e to the 2 minus 2t minus 1/2 e to the minus 2t. And this is for t greater than 1. All right, and so this is how you can deal with a discontinuous function as either one of your g or your p, right? In this case, p was fine, g was discontinuous. We can still solve it, right? We solve it separately on each continuous interval, and our information from the solution of the first interval gives us the initial value on the second interval, and we end up with this piecewise solution. Now, if you have a lot of discontinuities, many of them, then you just continue this process and you piece them all together at that point. All right, so let's take a moment now to talk about the main tool used in the proof of the general version of the fundamental existence and uniqueness theorem. We're not going to do the whole proof, but we are going to introduce this idea of what are called Picard's method, or so Picard's iterations, or Picard's method of successive iterations. And so this is a very useful way of thinking about these initial value problems. So here's the idea. Let's suppose we have an initial value problem of this form. So y prime is equal to f of ty, and then the initial condition is y of 0 equals 0. So let's just start with y of 0 equals 0 as our initial condition, and we'll talk later on in this lecture before we end about what to do with that before we quit here. But what to do with that if it's different than y of 0 equals 0. But here's the idea. So we have our first order differential equation, and let's also suppose that we have a solution to this, right? So suppose that phi of t, or phi equals phi of t, is a solution of the IVP. Then in this case, it turns out that phi also solves a certain integral equation. So it solves the integral equation given by the following. So here's the integral equation that phi solves. It's going to be, I'll write it with y's and then we can check that phi actually solves it. But first of all, it's going to be y equals the integral from 0 to t of f of t, we need an integration variable here, f of s, y of s, ds, right? So the whole idea here is that if phi is a solution, then when we plug phi in for y of this function here, right, then this function f becomes just a function of t. So plugging in phi equals phi of t for y in f yields the following, right? So it yields f of ty equals f of t phi of t. And so this function itself, this function f, can then be regarded as simply a function of t if we have our function phi that we know how to plug in for y. And so this term right here, which looks kind of wacky, this is actually a function of just s. All right, and so in this case then, if we look at our integral, we have our phi is equal to, on this side, we'll check this, right? But it's going to be equal to the integral from 0 to t of f of s phi of s ds. On one hand, phi of 0 is equal to the integral from 0 to 0. If it doesn't matter, right? Integral from 0 to 0 is going to be 0. So this gets our initial value checked off. Okay, so our initial value is a check. And on the other hand, if we take the derivative, d phi by dt, then by definition, this is d by dt of this integral equation. So f of s phi of s ds. And by the fundamental theorem of calculus, this derivative is just going to leave us with f of t comma phi. All right, and so there we have, again on this side, this is phi prime. And so there we have the other portion, the differential equation part of the initial value problem is also satisfied. So this idea that if a solution solves a differential equation, then it also solves a corresponding integral equation can be used to help us build a solution of the differential equation to begin with, okay? So here's Picard's idea. Integrals, remember, make functions nicer, right? So Picard's iterations, but I said Picard's idea. So we start with this initial value problem, right? Our initial value problem is y prime equals f of ty, and our initial value is going to be 0, 0 for now. Start with this, and then make a guess, okay? So make any kind of guess. So I'm going to pick a very poor guess, right? So the idea here is that we need to satisfy two things. We need to satisfy the initial value, and we need our function to satisfy the differential equation. So here's what we'll do. We will take our initial value and make this like our primary thing that we want to satisfy. So we'll make our initial guess be phi 0 of t, initial guess, right, is just equal to the 0 function. All right, and this automatically, of course, satisfies the initial condition. So the initial condition of phi 0 of 0 equals 0, well, sure, it's the 0 function, right? Now, this guess does not always work, but it does work a lot of the time. And if not, you can choose a different function, which, like in this case, you could choose phi of t equals t. And t, you know, when you plug in 0, you still get the initial condition satisfied. So, it satisfies the initial condition, but it probably does not satisfy the differential equation. And in most cases, it will not satisfy the differential equation. So at this point, we make a new, this is not going to work, right? It satisfies the initial condition, but not the differential equation. So what we can do is the following. We can make a new function. So use this to make a new function using the integral equation method that we just looked at above, right? So we'll say phi 1 of t is going to equal the integral from 0 to t of f of t with phi naught, so which happens to be 0, but I'm going to write it as phi naught of t with the previous one, right? But I need my integration variables here, so this should be s or u or something. All right, now this is a function, again, satisfies the initial condition, and it still probably does not solve the differential equation, but the fact that we've integrated our original guess is going to make it closer, actually, to solving this equation. And the theory of this is something that you'll study in a later course if you decide to go on with mathematics, but it's outside the scope of this course, the reason why this works, but the fact is that it does work. And Picard's method is then to iterate this process. So iterate this process. as follows. So you make the next function, phi sub n plus 1 of t, equal to the integral of f of t, again s, you need an integration variable, f of s with the previous approximation. So phi sub n ds, and in this process you'll then obtain a sequence of functions, phi 0, phi 1, phi 2, etc., and can keep on going forever, right? And so the idea is that as you continue this process on and on and on, that these functions get closer and closer to being solutions of the differential equation. They're all going to satisfy the initial value, the initial condition, because we've set them that way, and then we've set up the integral here, this equation, to continue that. By the way, this is something that we should, if you're going to write down one equation, it's going to be that one. All right. The idea, though, is that as you continue this process on and on, you get closer and closer to a solution, and the solution is going to be the limit of this sequence. And again, this is a kind of limit that we probably haven't studied yet, so we'll leave the details of why this works, and we'll do just some very simple examples in this class, but in general, we'll leave this for a later class, right? But Picard's method says, though, that the solution phi of the initial value problem is then given by this function. So phi of t is going to equal the limit as n approaches infinity of phi sub n of t. So continue this process on and on. It's like a limit. You go out, there's a function out there somewhere where all these approximation functions are approaching, and that function is the solution of your initial value problem. All right, let's do one together to see exactly how it works. And then we'll talk about what to do if the initial value is not 0, 0. But for our first one, let's use initial condition of 0, 0. So here we go. Y prime equal to 2t times 1 plus y. All right, and y of 0 equal to 0. Let's see how this works. Like I said, our initial guess, let's say phi 0. By the way, the f here, f of t and y, is exactly the right-hand side, right? So it's 2t plus 2ty. If we're going to write it out, I'm going to expand it out. Okay? So phi 0, we're going to guess, is just 0. All right? Because that satisfies the initial condition. It's very simple and straightforward. And let's see what happens for phi 1 then. So phi 1 is defined to be, by our process here, the integral of the previous one plugged into f, right? So this is going to be the integral from 0 to t of f, I'll write it in two steps on this one, but f of s with phi 0 of s ds. So this is the integral from 0 to t of f of s with 0 ds. And so that's going to be exactly this, right? Integral from 0 to t, f of s and 0. So this is just going to be 2s ds. And so this is just going to be, what, 1/2, 2 times 1/2 s squared, plug in t. So this is just t squared. T squared minus 0, right? So t squared. So phi 1 is t squared. And so now we repeat this, right? We repeat this. And so our phi 2 is going to be the integral from 0 to t of f of s with phi 1 of s ds. So that's going to be the integral from 0 to t of f with s. And then our function as a function of s. So s squared goes there, right? That's phi 1 of s. And then we plug all this into our function. What do we get? Integral from 0 to t of 2s. T's are s's, right? Plus 2 times s squared. So plus 2s cubed. ds. And then we're going to get back our t squared, and then we're also going to get a plus 1/2 t to the 4th. All right? Just by integration. All right, let's go to the next one. So phi 3, this is going to be the integral from 0 to t. We can just carefully plug in, right? So once we know how this process works, we just carefully plug into the integral. So it's going to be plugging in s's for t's, and then this whole thing for y, but as a function of s. So that's where it gets a little bit, you have to be a little bit careful. You're going to swap out s's for the t's here, and then put it all in for y up here. So the integrand is going to be 2s plus 2 times s times all this, right? So it's going to be 2s cubed plus, and then it's going to be just plain 1 s to the 5th. ds, right? We integrate. Notice what we're getting back here. We're getting back t squared 1/2 t to the 4th again, right? We're getting back exactly what we've already gotten from the previous parts. T to the 4th. Plus this one's now going to be a 1/6 t to the 6th. All right? And then we can iterate and do this again. So we'll do one more together and you see exactly how this works, right? So yeah. So phi sub 4 is going to be integral from 0 to t of 2s plus 2 times s plus each of these, right? So 2s cubed plus s to the 5th. That's all the stuff we had before. Now it's just adding one term. It usually turns out to work this way. So, I mean, you don't ever want to say that it's always this way. But this is pretty much how it works out. So that becomes s to the 7th. And then when we integrate through, we get t squared plus 1/2 t to the 4th plus 1/6 t to the 6th plus, this is now going to be 1/21st, right? No, 1/24th t to the 8th. And then it continues on and on like this. All right, so we'll leave this one here, especially, so sometimes this one probably we could figure out that this pattern involves, you know, probably cosines. It looks like even powers, right? Maybe an exponential, some cosine, something like that. Sometimes you can find a pattern, but for us, for this class, we just want to make sure that we understand the method and exactly how it works. And so we'll say that phi of t, in this case, is going to equal the first few terms, but t squared plus 1/2 t to the 4th plus all these terms that keep showing up, they're going to be there in the limit, right? T to the 6th plus 1/24 t to the 8th plus, and then it's just going to continue, right? So we'll write it like this. But this is still an approximation. If you cut it off right here, that's not the solution. It won't solve the differential equation. It'll just be an approximation. But that's okay. I mean, you'd have to write that it's an approximation at that point. But if you put the dots, then we understand that this came from the Picard iteration method and that this is just one step along the way. All right, so here's the last question. What if the initial condition is not 0, 0? All right, so we'll do this one by an example, but let's suppose that we have differential equation of the form dy by dt equals, not too crazy, but t squared plus y squared. And then the initial condition, though, is y of 1 equals 2. All right, and so the idea is that we want to translate. We want to basically make new variables, but translate this to a new coordinate system. All right, so we want to basically make some substitutions. So we're going to let u equal to t minus 1, so that when t is 1, u is 0. All right, so that u of 1 is equal to 0. Similarly, we want to change this, right? So we're going to let v equal y minus 2, so that v of 2 is also equal to 0. All right, and in this translation, though, we have to change everything. We're going to get our initial condition to be 0, 0. V of 0 equals 0, right? V of u equals 0. But these things need to be, so the t and the y need to be written in terms of u and v up here, right? So part of our translation is going to be solving for these. So t is going to be equal to u plus 1 in this case, right? And y is going to be equal to v plus 2. And our new initial value problem that we solve is going to then be dv by du. And you can, by the way, because these changes are just translations, you can check that when you do the chain rule and take the derivatives, you end up with the same exact differential on the left, right? Derivative on the left here. And this will end up being u plus 1 quantity squared plus v plus 2 quantity squared. And now our initial value is v of 0 equals 0, where this 0 represents the u variable and this is the v. All right? And so then you can apply the Picard method to this equation. And the only difference is that at the end, you'll have to translate back, right? Translate back to your t and your y plane. Everywhere you have a u or a v, you'll have to translate. Okay, so you shouldn't end up with too many v's on the right-hand side after the integrations, but you will end up with u's. So u's and v's both need to be translated back in this case. So that's the idea. I'm not going to do it because this gets very messy very quickly. You can do the first couple if you want, just to see how messy it does get, because for a couple of reasons, but especially because this v term is squared and there's sums here, and it's not hard, but it is tedious. It gets pretty messy, and then at the very end you have to remember to translate everything back, right, to the YT plane. So you'll see those kind of problems in your homework as you work on this. So I'll leave that for then, and I'll talk to you guys in the next lecture.